Hello class, welcome to lecture 8.1. Today we're going to be doing constrained optimization using substitution in two examples. So in the meme in the background, this guy is smashing the elimination to solve a system of equation, or substitution to solve a system of equations essentially. And yeah, so we'll just get into it. What we're doing now is I've shown you where the optimal bundle is. It's this tangent point on the indifference curve and the budget constraint where the slope of the indifference curve, the marginal rate of substitution, equals the marginal rate of transformation, which is the slope of the budget curve. So you can see that in here. And what that means is your willingness to substitute for an additional good equals your ability to trade off for another good. And we need to have a formal way to solve for this optimal bundle, this the most happiness that a consumer can get given their preferences, their income, and their prices. And so we're going to do this using calculus. And so this is kind of the formal statement of the problem, right? So we're maximizing, we're doing optimization here. So we're trying to get the highest utility, maximizing the utility as a function of the amount of good 1, Q1 that we're consuming, and the amount of good 2 that we're consuming, Q2. And so this Q1 and Q2 underneath the max just means that we get to pick Q1 and Q2, or Q1 and Q2 are our choice variables. All right, and so we're subject to this ST, you'll see me abbreviate, a budget constraint, which is this equation number 2. And our budget constraint is just the amount of income we have, which is Y, and the prices of the two goods, which is P1 and P2, and the amount that we choose to consume, Q1 and Q2. And so we've got two choice variables, and then we've got Y, P1, and P2 are exogenous parameters, ones that it doesn't matter what we do, those are just going to be set. And so we have 1 is our objective function, it's the utility function, we want the highest amount of utility possible, and 2 is this objective function, it's our budget constraint. It tells us what our income is, what the prices are, and what the total set of possible bundles that we can actually afford are. And so we want the highest utility subject to having to choose a bundle that we can afford. And so let me just put those in the plot for you real quick, right? So number 1 is the objective function, like I said in the last slide. And this is just graphically depicted by these utility curves, right? These indifference curves right here, on which each indifference curve has equal utility. And so we know that IH is going to have more utility than I no subscript, because we know that more is better, that a larger amount of good 1 and good 2 is going to be preferred to a lesser amount of good 1 and good 2. And on all kind of the points of indifference curve H, there's a more combination of good 1 and good 2. And so we're trying to reach the farthest indifference curve away from the origin so that we can be the most happy, as happy as possible, right? So we would take indifference curve infinity if we could reach it. But the problem is we're subject to this budget constraint, which is this line right here, this gray line right here, which I covered last class. And it just tells you, okay, if I spend all my money on good 2, this is the amount of good 2 I have. And if I spend all my money on good 1, this is the amount of good 1 I have. And so I can have any combination of good 1 and good 2. And anything basically outside this gray line to the right of it is unaffordable. So all these bundles out here are unaffordable given our income and what the prices are. And so we're looking for Q1 and Q2 such that our utility is the highest it can be, such that given our income and given our preferences, this is the highest amount of happiness we can get. And we need these optimal Q1s and Q2s. And we can do that with the information we have to satisfy the condition that the marginal rate of substitution, the slope of the indifference curve, equals the marginal rate of transformation, the slope of the budget constraint. And if we get the point where those two are tangent or touching just once, then we have our optimal Q1 and Q2. And so I'm going to do basically an example problem. But I want to show you kind of the most abstract way to solve this, and then I'm going to dive into a numerical example. So the hard part is choosing two variables. Max your utilities subject to some income and prices, but you have to choose a good one and a good two, the amount of both. And so, but we have two equations, just like you may have seen before. High school algebra covers this. And so we've got kind of two unknowns, Q1 and Q2, and two equations. So we're just going to solve for Q1 in terms of Q2 and make this into a single variable calculus problem. And so how we do that is we just take our budget constraint here and we just solve it for Q1. So what are we going to do, right? We're going to do y minus P1 times Q1, and then we'll have y minus P1 times, or y minus P2 times Q2, and then just divide by P1, and we have Q1. And we can go in here, and this would be Q1, but we know that Q1 is y minus P2 times Q2 over P1. And so now all we have to do is maximize our utility, choosing Q2 subject to this budget constraint. And so it becomes an easier problem where we just need unconstrained optimization from Calc 1 after the substitution. And so let's do a numerical example. And this is number 23 on page 95 of the book. And we know that Veda likes spare ribs and R and fried chicken C. Her utility function is 10 ribs squared times chicken. Her weekly income is $90, which is only spent on chicken and ribs. If the price of ribs is $10 and the price of chicken is $5, what's her optimal consumption bundle? How much ribs and chicken should she consume? So, and we were going to want to show her budget line, her difference curve, and the optimal bundle in a diagram. So let's start by making the diagram, because I actually think it's first to ground ourselves in what the problem is. And so here is some representative, potentially indifference curves for Veda. And her budget constraint is drawn here in this gray line. And so if she spends all her money on good two, which is chicken, she can have 18 chickens. Where if she spends all her money on ribs, then she can have 9 racks of ribs. And so this is her budget constraint here. And we're looking for this point so we can finish off our diagram. And so we can know what bundle of goods Veda should choose to maximize her well-being. And so here's the setup of the problem as you saw earlier. And so we're going to maximize her utility as a function of chicken and ribs. We're going to choose chicken and ribs. And this is the actual utility function here. Subject to her budget constraint, which is just her income of 90, equals $10 for each rib she buys and $5 for each chicken she buys. And so what we're going to go through here do is solve this using substitution and calculus. So let's start by just solving equation 6 for C. So what am I going to do? I'm going to subtract 10R, and then I'll have 90 minus 10R equals 5C, and then I can divide by 5 and solve for C, and I get 18 minus 2R. So C equals 18 minus 2R, and now I have something that I can plug into equation 5 to make it a single variable problem. And I just plug in C equals 18 minus 2R for C up here, and I have utility equals 10R squared times 18 minus 2R. That's what C was. And I'll go ahead and simplify that to make it easier to take the derivative of that. And so I factor through the 10R squared, and I get utility equals 180R squared minus 20R cubed. Great. All right, so everyone should have seen that already at some point in their academic career. And so now we have to do some calculus to figure out what the optimal amount of ribs is. And so what we do is to find the extrema, that is the minimum and the maximum points of our function, what we do is take the derivative with respect to r of this function. And so because this is an additive function, all we need to do is use the exponent rule here. And so 180r squared becomes 360r. You multiply 2 times 180 and subtract 1 from the exponent, and you get 360r minus 60r squared, which is just 3 times 20, and then subtract 1 from the exponent. You get minus 60r squared. And so that's great. Now we have the derivative with respect to r. So this is the slope of the utility function as r changes. And so we know that at a maximum or a minimum point, the slope is 0. And so what we do is we just plug in 0 slope and then figure out at what r there's a 0 slope. And so we've just made du dr 0 and solved for r. So what I did was I factored in r out, and I got r times 360 minus 60r, equals 0. And then if you solve this, you get r is either 0 or 6. So you know that these are the extreme points of the function, and that at least one of them will be a utility maximizing bundle. And so I'm going to get into that as we go along, but I just wanted to show you the finished diagram first. After we plug in C, by plugging in R into the budget constraint. So what I do is I take this 6, this is 60 plus 5C, and then I can solve for this, and I get chicken equals 6. Let me, is that right? 90 equals 35C. Chicken should equal 6 too, so it should be 6, 6. I apologize for the error there. But anyway, so this is a 6 and this is a 6, and you can see that we have solved for the optimal bundle for beta. Is 6 chickens and 6 slabs of ribs. So I did is I solved page 95, number 25, part A. I encourage you to solve part B by yourself, where the prices are changed to $10 for ribs, $10 for chicken. What about r equals 0? Why did you just discount that? Well, I want to show you exactly why. So I said that when you set it to 0, you can find the extrema of function, which is either the maximum or the minimum. And so what we need to do is we need to guarantee that the points that we found are actually a maximum. That is, that the function of our happiness is maximized at the point that we found, the critical values, the r equals 0 and the r equals 6. And so if the second derivative is negative, then we have found a maximum. And that's good. So we want to find that plugging in our answer to the second derivative of the utility function, the number is negative, which means we have a maximum. And so what we do is we check the second derivative for the solution to be a maximum. So what I do is we've got the utility function here is 180r squared minus 20r cubed. The first derivative, which I showed you earlier, was 360r minus 60r squared. And the second derivative is just 360 minus 120r. So pretend this r is to the first power. 1 times 360 is 360. Takes 1 off the power. R to the 0 is 1, and you get 360. And I'm not going to do this one, but by the same logic. And so when I plug in 6 to the second derivative, I get 360 minus 120 times 6. This should be negative 720. And so the value is negative 360. So we know that 6 has to be a maximum because this number is negative. And so when I plug in 0 to this, which was our other possibility for r, I found that 360 minus 120 times 0 is well, this should just be positive 360 because this cancels, and I get 0 is a minimum point of the function because this number is positive. And so you need to remember to always check the second derivative for the solution to be a maximum. Otherwise, you might have found a utility minimizing point, which is not what we're trying to do as consumers. So just to give you some extra intuition on the project, let's say that, remember that our utility function as a function of ribs and chicken is 10r squared times c. If you put 0 in there for r, as we found, this utility number is 0, regardless of what you put in there for c. So that's another way to think about it, to gain some intuition on the problem. But anyway, in this video, I've given you a very quick example of how to solve for the utility maximizing optimal bundle using the substitution method. And we're going to do an alternative method in the next class, which is the Lagrangian method, which is kind of the brute force way of getting through it. And it typically requires a little more cleverness when it comes to like the math when you do that, because you have to use substitution usually to, or what's the other one? I forget what the other one is. The one at the beginning of the video to solve it. And there's a lot of, actually, like, there's a lot of applications for this, and primarily we will use this method to derive demand curves. So if you're ever really wondering where like the hardcore decision theory is behind a demand curve, we'll be doing that next, or not next exactly, but very soon. And something I just want to like emphasize at the end of this video is this is really a lot harder to do than I've shown you, than I've made it seem, perhaps, in this first one. Even if you think it already looks hard, it's probably harder. So I really encourage you guys to practice these questions a lot and get started with them early on your homework, and to come see me in my office hours after you've tried it at least once, because there's a lot there could be a lot to iron out here, and this will be on your next quiz. So yeah, practice a lot. And I'm sorry for not releasing this a little bit sooner, but I wanted to give you one more example that was a little more abstract, and I wrote it down in the appendix here, which you can kind of start to take a look at, but I really frustrated with it yesterday, and that's why I didn't release the video. But it kind of follows the same logic. The thing that's harder is that the utility function is a quotient, and there's a multiplicative relationship on the top. And so when you do the derivative of this thing, it gets really ugly, but everything else is the same. Look, we are substituting to solve for either Q1 or Q2. I solve for Q2 here, and so I just plug this back into the utility function, and that's what the utility function looks like now. And then I just take the derivative of that, and yeah, here's the derivative of that. And to solve for Q1, you would set this equal to 0, and then you need to factor everything out to get Q1 on one side. So I was having a little frustration doing that, but it is possible. And yeah, so I'll keep working on it, and hopefully have an answer to that one to update you in the future. Thanks for listening, and I will see you for 8-2 on Thursday.